This is AQA A-level chemistry topic, and we're looking at a year 13 topic, acids, bases and buffers. So this is part 1, and we're going to look at a general introduction to the topic. If you get a chance, I recommend that you pause, have a go at the activities going through this and test your own knowledge to see what's going well and what might need a little bit of work. So within this section, we're going to look at defining an acid. We're going to look at the Bronsted-Lowry definitions. We're going to see what happens in acid-base reactions, and we're also going to introduce the ionic product of water. So let's jump straight to some definitions. The Bronsted-Lowry acid and the Bronsted-Lowry base. How do we define them? Well, a Bronsted-Lowry acid is a proton donor. Remember, when we talk about a proton, we're talking about an H plus ion, and that fits with what we know about hydrochloric acid, HCl, nitric acid, HNO3, sulfuric acid, H2SO4. They all have protons that they can donate. And the base is the opposite of that, so it's a proton acceptor. Moving on then, let's have a look at some of these, and you simply have to look at them and decide what are the reactants acting as. Are they an acid or are they a base? So it starts off fairly straightforward. We've got sulfuric acid. Of course, that's an acid. We know that sodium hydroxide is a base. It's probably the first one you learnt about. So straight away, job done, we're ready to move on to the next one. And similarly, we've got hydrochloric acid here, which we know is a strong acid, and we're going to look back at that more later within this topic. And we know that hydroxides generally are alkalis and therefore bases, so we can identify both of those. Gets a little bit more unusual as we move down to the next one. We've got HCl, which we're immediately going to think is an acid, and we've got H2O, which we think of as being neutral. But let's look at it in the context of the definitions. The HCl has become Cl-. It's donated a proton, definitely acting as an acid, but the H2O has accepted a proton to become H3O+. So in this context, the water is acting as a base. Similarly, if we look at the next one, we have got NH3 accepting a proton, becoming NH4+, which makes it a base, but here the H2O is donating a proton, becoming OH-. So the water in this case is an acid. And then we get to one that, if you've done work in aromatic chemistry, you'll already be familiar with. Sulfuric acid and nitric acid. Both acids, but one of them is acting as a base. And we can see that the sulfuric acid has donated a proton. It's become HSO4-, but the nitric acid has actually accepted a proton to become H2NO3+. So nitric acid here is a base and sulfuric acid is the acid. And on the bottom one, two water molecules coming together. One of them's accepted a proton, one of them's donated a proton. Take your pick. It is happening that some water is acting as an acid and some water as a base. So let's move on. Slightly different question now, see how you do. And we're going back to basics here. We're looking at an H plus ion. How many protons, how many neutrons, how many electrons? And it's really quite simple. It's got one proton, atomic number 1. It's got no neutrons because its mass number is also 1. And it has 0 electrons because it's positively charged. It's lost its electron. Now, it's really not possible for a hydrogen ion to exist in isolation. It's a naked proton. It's far too attractive and it will bond with something. Now, commonly when we talk about acidity and aqueous solution, we end up with the H plus ion bonding with a water molecule to make an oxonium, sometimes called a hydroxonium ion. So what do we think it's going to look like? We can now look at it in the context of bonding. What would the dot cross diagram be? Well, we know that H2O and H plus will make H3O+. That's our oxonium or hydroxonium ion. Let's build our water molecule as a dot cross diagram. You can see the crosses coming from the H's. I've got 2 bonding pairs, 2 lone pairs. But I've got an H plus ion coming in with no electrons. So that's going to form a dative covalent bond using one of those lone pairs. And once we've got that, to finish the diagram, we need to remember that it's now charged. So square brackets with a plus sign. This would be trigonopyramidal. It would be a bond angle of 107 degrees. So cross links once again with other topics. So let's move on and think about the ionisation of water. Work your way through these questions, then we'll review. So if I were to think about the ionisation of water, breaking it down into its ions, I'm going to start with liquid H2O, and I am going to end up with H plus and OH minus. You can see here that that should indeed be reversible. That went well. Reversible there, because it does go in both directions. Similarly, the next one is reversible as well, so I'll change the arrow in a second, but the reality is that the H plus ion doesn't exist, so the 2H2O will break down into an H3O plus and an OH minus. So we need to be familiar with both of those formats, but we're interested in the top one predominantly for what we're about to do. And now I want you to link this back to our equilibrium work that you've done in year 12 and in year 13. What would the expression be for the dissociation of water if we're dealing with the first one that we did, 1H2O going to H plus and OH minus? Well, for Kc, we've got to remember that we have product over reactants. If we're dissociating, that means the ions go on top and the H2O goes on the bottom. And we have got one or two assumptions that we make when we consider the dissociation. In part, we need to think about where the equilibrium will lie. If I've just got a bottle of water, do we think there's going to be a very high concentration of water and a very low concentration of ions? Do we think the reverse is true, or do we think it's somewhere in the middle? The reality is that very little dissociates. If you've got a bottle of water in front of you now, the majority of it is water molecules, but a tiny, tiny number of them will be dissociating into H plus and OH minus in an equilibrium reaction. So hold that thought and think about the activity here. Now, what we can say, because we know the equilibrium lies so far to the left, we actually assume the H2O concentration is so large that we can say it's constant. Any change made to it will have a negligible impact on any Kc value. So when we talk about Kw, we actually mean Kc multiplied by H2O, but it's possible to do that because we're totally ignoring the concentration of H2O. What that means is that we've got an expression that you need to learn for Kw, derived from that Kc expression, but Kw is actually concentration of H plus multiplied by concentration of OH minus. So then we think about what its units will be. Well, we've got concentration multiplied by concentration. That's mol dm to the minus 3 times mol dm to the minus 3, which is mol squared dm to the minus 6. So a couple of very basic calculations to do here. Kw is temperature dependent, but you have got to learn that at 298 K it has a value of 1.00 by 10 to the minus 14. So with that in mind, have a go at the calculation below. So I'm going to start by writing out my expression for Kw. It's H plus times OH minus. I want to know the OH minus concentration, so let's rearrange to make that the subject. I know that Kw is 1 by 10 to the minus 14 because this is happening at 298 K, and we're told that the acid has a concentration of 1 by 10 to the minus 4. I then simply need to put those numbers into my calculator, and I get to an answer of OH minus concentration is 1 by 10 to the minus 10 mol dm to the minus 3. So let's do another calculation just like that. I've started you off with the Kw expression. This time we're calculating H plus, so we rearrange slightly differently, but this time it's Kw over concentration of OH minus. We put the numbers in that we're provided with. Kw that we have to learn, 1 by 10 to the minus 14, divided by concentration of OH minus, 3 by 10 to the minus 7. Take that calculation through and we get to an answer of 3.33 by 10 to the minus 8 moles per decimeter cubed. These calculations we're looking at now are going to become steps in much bigger calculations later, so getting a handle on these basics is going to be incredibly important. Slightly different question, but it's one that gets you thinking. What is the concentration of water? So guiding you through this, the mass of 1 decimetre cubed of water, knowing water has a density of 1 gram per centimetre cubed, is 1000 grams. And we know its molecular mass is 18. So if we know its mass and we know its molecular mass, we can work out the number of moles, 55.5. And therefore the concentration of water is 55.5 moles per decimetre cubed. Let's go back and do a little review to end this video. What would we form if each of these species accepted a proton and by doing so therefore acted as a base? Well, OH minus plus a proton takes us to water, H2O. H2O adding a proton goes to H3O plus, the oxonium ion. NH3 gaining a proton goes to NH4 plus, the ammonium ion. And Cl minus would be HCl, hydrochloric acid. So that takes us to the end of video 1. Thank you for listening and goodbye.